Asteroids are not hypothetical threats. Earth has been struck many times in its history. 66 million years ago, a large asteroid impact contributed to the extinction of the dinosaurs. The crater it left, Chicxulub, spans more than 150 kilometers. But extinction-level events are rare. More common are smaller impacts. In 2013, a 20-meter object exploded over Chelyabinsk, Russia. The airburst released energy equivalent to hundreds of kilotons of TNT. Windows shattered across the city. Over 1,000 people were injured, mostly from flying glass. That asteroid was not detected before impact. It approached from the direction of the sun, making ground-based optical detection nearly impossible. This event demonstrated something important. Even relatively small objects can cause significant regional damage. Planetary defense is not science fiction. It is risk management. Humanity cannot prevent asteroids from existing, but it can detect them, and perhaps, if necessary, change their path. Most asteroids orbit harmlessly in the main belt between Mars and Jupiter, but some are categorized as near-Earth objects, NEOs. These objects have orbits that bring them close to Earth's path. Among them, a subset is classified as potentially hazardous asteroids based on size and orbital distance. Size matters. An object 10 meters wide may burn up in the atmosphere. An object 100 meters wide could devastate a city. An object 1 kilometer across could cause global consequences. Detection efforts have improved significantly over the past few decades. Space agencies track thousands of known NEOs. But detection is not the same as defense. Knowing an asteroid exists does not change its orbit. The next step required testing whether a small velocity change could alter a future trajectory. That is where the mission began. DART was not sent to a threatening asteroid. It was sent to a test system. The binary asteroid system Didymos consists of a larger primary asteroid and a smaller moonlet called Dimorphos. Dimorphos orbits Didymos at a predictable rate. By targeting the smaller body, scientists could measure any change in orbital period after impact. This was essential. The goal was not to destroy the asteroid. It was to alter its motion slightly. The test had to be measurable, repeatable, and safe. Didymos posed no threat to Earth. That made it the ideal laboratory. Deflecting an asteroid does not require a dramatic explosion. It requires time. If an asteroid were discovered decades before potential impact, even a tiny change in velocity, on the order of millimeters per second, could shift its future position by thousands of kilometers. Orbital mechanics amplify small changes over long timescales. DART tested the kinetic impactor method. Instead of using explosives, the spacecraft would collide directly with the asteroid at high speed. The momentum transfer from the impact would alter Dimorphos' orbital period around Didymos. The key question was not whether impact would occur. It was whether the change would be measurable. Humanity was about to test planetary defense not through theory, but through controlled collision. On September 26, 2022, the DART spacecraft completed its mission. It did not land. It did not orbit. It collided. Traveling at approximately 6.6 kilometers per second, DART struck Dimorphos head-on. The spacecraft used autonomous navigation in its final hours. As it approached, onboard cameras locked onto the asteroid, correcting its trajectory in real time. The final images transmitted showed Dimorphos growing rapidly in frame, a rocky surface filled with boulders. Then the signal ended. Impact. This was the first time humanity intentionally changed the motion of a celestial body. But the mission was not about spectacle. It was about measurement. The question was simple. Did the collision change Dimorphos' orbit around Didymos, and by how much? DART did not operate alone. Telescopes around the world observed the collision. Space telescopes, ground-based observatories, and radar systems tracked the event. When DART struck Dimorphos, a plume of debris erupted into space. This ejecta was critical. The debris carried additional momentum away from the asteroid, increasing the deflection effect beyond the spacecraft's impact alone. Astronomers measured changes in brightness and orbital timing. Before impact, Dimorphos orbited Didymos once every 11 hours and 55 minutes. After impact, scientists began carefully timing each orbit. Within days, preliminary results showed a measurable change. But precision required weeks of data collection. Planetary defense was not judged by the explosion. It was judged by the clock. The final measurement was clear. Dimorphos' orbital period had shortened by approximately 33 minutes. This was far beyond the minimum success criteria of 73 seconds. The impact worked. The spacecraft alone transferred momentum. But the ejected material amplified the effect. This revealed something important. Asteroid deflection efficiency depends not only on impact speed, but on surface composition and structure. Dimorphos appeared to be a loosely bound rubble pile. That structure allowed more material to be ejected, increasing the deflection. The mission did not simply prove that an asteroid can be nudged. It provided real data about how different asteroid types might respond to kinetic impact. Planetary defense moved from theory to experiment. DART was a small spacecraft, but its significance was planetary. It demonstrated that humanity can detect, target, navigate to, and alter the orbit of a small celestial body. This capability required precision guidance systems, deep space communication, orbital modeling, global coordination of observation. The mission did not eliminate asteroid risk, but it proved a method. Future missions could use similar techniques, with adjustments for larger objects or different compositions. Planetary defense is now a tested engineering discipline. The universe will continue sending asteroids near Earth. But Earth is no longer passive. For the first time, humanity demonstrated it can change the trajectory of a natural object in space, deliberately and measurably. DART proved that an asteroid's path can be altered, but there is a critical condition: time. A small velocity change works only if applied years, or decades, before a potential impact. If an asteroid were discovered only weeks before collision, deflection would be nearly impossible. That means detection is the foundation of planetary defense. Surveys continuously scan the sky for near-Earth objects. Ground-based observatories track known asteroids, refining orbital predictions. New space-based infrared telescopes are being developed specifically to detect objects that approach from the direction of the Sun, the same blind spot that allowed the Chelyabinsk object to go unnoticed. Planetary defense is a two-step process. Find them early. Change their path if necessary. DART addressed the second step. The first step remains equally essential. Dimorphos was a rubble pile asteroid. Its loosely bound structure amplified the deflection. But not all asteroids are built this way. Some may be solid monolithic rocks. Others may have metallic cores. The efficiency of kinetic impact depends on composition, density, internal cohesion, and rotation. Future missions will study asteroid structure in greater detail to improve predictive models. Understanding internal composition is as important as tracking orbit. The DART mission was followed by the European Space Agency's Hera mission, which will return to the Dimorphos system to measure the impact crater and internal structure directly. Planetary defense is now iterative. Test, measure, refine. The more we understand asteroid physics, the more reliable future deflection strategies become. Kinetic impact is one method, but it is not the only one studied. Other theoretical approaches include gravity tractors, spacecraft that hover near an asteroid and use their gravitational pull to slowly alter its orbit. Nuclear deflection has also been studied, though it carries political and technical complexities. Each method has trade-offs. Kinetic impact is relatively simple and scalable. Gravity tractors require time but offer precise control. Nuclear options provide higher energy but greater uncertainty. DART was chosen because it was feasible with current technology and posed minimal risk. Planetary defense planning now includes a range of strategies, each evaluated based on object size, warning time, and composition. The goal is not a single solution. It is preparedness. For most of human history, asteroid impacts were unavoidable natural disasters. We had no awareness, no tracking, no response. That changed in the late 20th century with systematic sky surveys. And it changed again in 2022 with DART. The mission did not eliminate risk, but it shifted perspective. Asteroid impacts are now a measurable hazard with tested mitigation techniques. This does not mean every future threat is solved, but it means humanity has moved from passive observation to active capability. We cannot control the cosmos, but in limited, precise ways, we can influence our environment within it. DART was not a weapon. It was a proof of concept. For the first time, a natural celestial orbit was intentionally altered by human design. Planetary defense is no longer theoretical. It is operational science.